Hello everyone, my name is Brandon Griffin, and today we are going to be talking about correlation and regression. So first up, we have to answer the question, what is correlation? You've probably heard the term correlation before, and you know that it has something to do with the relationship between two variables, but what exactly does it mean? Correlation is a measure of the direction and the strength of the relationship between two variables. So it does two things. It measures the direction and the strength of two variables. The direction of this relationship can be positive or negative, or there could be no relationship, or there can be a weak or a strong relationship. And I'm going to provide a few examples of this. So first off, a positive relationship, an example of a positive relationship would be when hours spent reading per day increases, the ACT score increases as well. And that makes sense. So when you're reading, you're using your brain, you're using your mind, you're doing something that's more academic oriented. It's just going to make sense that your ACT score increases. And the data between hours spent reading and your ACT score shows that there is a positive relationship between reading per day and ACT score. An example of a negative relationship is when daily steps increases, body weight is going to decrease. So for example, in the second chart right here, we can see on the variable A, this could be number of steps per day, or maybe the average number of steps per day, and the variable B could be body weight. So the more steps that you get per day, your body weight's going to decrease. And something about correlation. Correlation is the relationship between 2 points of a line. But it doesn't mean that people are going to, be perfectly correlated or perfectly related. So if we look at this bottom graph right here, this is the average line, or this is the average correlation that we get between these two variables. But there are people, who walk a high amount but have higher body weights versus some other people. So it is the general trend between two variables, and there can be outliers, there can be things that are a little bit differently, but the way that correlation is calculated and how it is put together is generally there is going to be a positive relationship. So for a positive relationship, when one variable increases, the other variable increases. For a negative relationship, when one variable increases, the other variable decreases. So positive is when they move together up, and negative is when one increases, one decreases. So they, move kind of in not necessarily different directions, but when one increases, one decreases. So they are correlated, so they do move together. So that is the direction of the relationship, and now we need to talk about the strength of the relationship. A statistic called Pearson's R is used to assess the strength and direction of a relationship. So this statistic. So in our ACT and reading example, they were very highly correlated. And we could have calculated a Pearson's R correlation statistic, and it would have ranged anywhere between -1 to +1. 1 would mean that there is a perfect relationship between hours spent reading and ACT score. A 1 hour increase is going to lead to a 1 point increase in ACT. They're going to be perfect. And the same with number of steps and body weight. So maybe every 1,000 steps increase, body weight's going to decrease on average by 10 pounds. So there are different levels of the strength of this relationship, and they range from -1. So -1 would be perfectly negative. +1 would be perfectly positive, very strong. So two variables can be related, and they can either be kind of related or they can be very strongly related. So at the top left here, we have a perfect correlation. We can see that as one variable increases, another variable increases perfectly and by the same distance. So they're all along this line. In the top right here, we have our Pearson's R that's close to +1, where everything generally follows this line, but things can deviate just a little bit above or below this line. But in general, they follow this line very close. Conversely, this is a R value that's close to -1, so there's a strong negative association. So as one variable increases on this x-axis, we can see that it decreases on the y-axis, not perfectly, like this variable right here is, kind of above that line. This one's below the line, but in general, as one increases, the other variable decreases. An R value of 0 means that there, or close to 0 means that there is a weak or no association. So for example, maybe this could be the amount of water you drink and your desire to watch TV. Maybe there's some sort of relationship, but we can see as amount of water increases, desire to watch TV isn't really affected at all. So that'd be an example of a weak or no association. So one thing that you have to realize when talking about correlation is correlation does not imply causation. And what does that mean? It means just because two variables are related does not mean that one causes the other. So we saw that reading time, is going to increase your ACT score. That makes sense in general that, reading time would increase ACT score. But just because two things are related doesn't mean that one causes the other. And a relationship that seems causal or is correlated but is in fact not is called a spurious relationship. And let's look at an example. So two variables that seem to be causally related but are not are the divorce rate in Maine and the per capita consumption of margarine. So we see that in the year 2000, the per capita consumption of margarine and the divorce rate in Maine, was relatively high. And as the years went on, they decreased almost in tandem, very close to each other. So the margarine consumption decreased all the way from 8-9 pounds down to 2 or 3 pounds. The divorce rate decreased from about 4.95 all the way down to 4. So just because the divorce rate in Maine and the per capita consumption of margarine are related doesn't mean that one causes the other. This is kind of, you have to stretch your brain a little bit to think of a relationship. So maybe in Maine, margarine is like the biggest deal in the world. Or maybe it's a bad thing to do. So the more, you eat margarine, that's a deal breaker in the relationship. That's a deal breaker in the marriage. You're going to have higher divorce rates. So as the per capita consumption of margarine or the per person consumption of margarine decreased, maybe the deadly sin of eating margarine, means people are going to, stay married longer. So this is an example of a spurious correlation. So even though they are related, they are not causally related. 99.9999% sure that the divorce rate in Maine and the per capita consumption of margarine are not related. But it's cool to look at examples like this. Other ones, there's one about Nicolas Cage movies, and I think it's crime rate, something like that. But this is an example that correlation does not imply causation. So an example of correlation, it is great for summarizing relationships and assessing how two variables move together, and it's the direction and the strength. So they can be positive or negative, and they can be weak or strong, and everything in between. One thing about correlation is it does not address cause and effect. And 3, it cannot really be used to forecast the future. And this is where regression comes in. And you may have heard regression, but we're going to talk about it and go through it today. Regression is a statistical method used to determine the relationship between two variables, that's misspelled, two variables, by assessing how the independent variables or the x variable predicts the dependent variable or the y variable. So with correlation, we just had two variables. One was not an independent variable or the y variable. One did not come before or after the other. They were just two variables that were there. In regression, we set one variable as the independent variable. That is the predictor or the thing that, we think is going to explain something. The y variable is our dependent variable or the outcome or the thing that we are trying to explain. So continuing with our, reading example and ACT, or reading, time spent reading and ACT. In this example, we might want to put, hours spent reading as our x variable, and then the outcome or the thing that, number of hours spent reading causes is an increase in ACT score. But let's look at some examples after we keep talking about it. So there are multiple types of regression, but the one that we're going to talk about in detail today is going to be simple linear regression. And in a simple linear regression, we use one independent variable to predict one dependent variable. And we're talking about linear regression. So that is just a line. So the relationship doesn't curve, it doesn't, have any different shapes. It's linear, where in general, As one variable increases, the other's going to decrease, or if one increases, the other one's going to decrease. There's no polynomial or curvilinear relationship. This is strictly linear regression. So in a simple linear regression, we use one independent variable, an x variable, to predict one dependent variable, or y variable. And a regression analysis will produce a regression equation that lays out the relationship between the variables. So what is regression? If we lay out the formula for regression, we see that it is y hat, that's this, this arrow above the y hat, meaning the estimated value of y equals a plus beta x plus our error. And I'll dig into this a little bit simpler, but this is the equation for regression. So what we're doing with regression is we are finding the estimated value of our dependent variable. We have a constant, or a y-intercept, and then we have a slope, so how much increase or decrease in our dependent variable caused by our x variable, and then we have some type of error term. So let's bring this back just a step. That is the complex equation for regression. Let's think about what a line is. If you think back to your high school math, what is a line? A line is y equals mx plus b. So what is y? Y is the line. What is mx? Mx is the slope. So that is how much up or down, or the steepness of your line. And b is the y-intercept, so where it starts. So think about regression as y equals mx plus b. And all that, the y hat, and this, a beta, this alpha beta, and this error term, are essentially just the statistical notation of how to write this regression equation. But to think of it simply, you can think back to your high school math class that y equals mx plus b, and that will make things a little bit easier to understand. So we are given the formula for a line in regression, and the slope of the line is the beta, and the y-intercept is this a value. So it's similar to y equals mx plus b. And once we get into our assignment for this week, talking about regression, I'll show you examples of this and more detailed interpretation statements. So how can you tell if a regression equation is good or not? So just like with regression, there are values to assess if a regression equation is good or fits the data well. So with correlation, we used the R value, the Pearson's R correlation coefficient. That ran from -1 to +1. The higher or lower it was, the better fit it was going to be. So in regression, we use something called the squared correlation coefficient, or the R square value. And essentially what an R square value tells us is the percentage of variability in the y variable that is explained by the x variable. So a low R squared means that the independent variable x does not explain everything about the dependent variable y, which means that there are other factors determining the effect of x on y. So if we look at this top right graph here, we can see that all of these dots right here are not very close to this red line, to our regression equation. So if we look at our R squared, we can see that it says 14.7%. So that means there are lots of other things that are impacting the relationship between our x variable on our x-axis and our y variable on our y, axis. Another way that you can think of R squared is the percent of the story that it tells you. That's one way that I think about it. So if we see R squared of 14.7%, you can think about it like we know 14.7% of the story. So that's, like 1/8 of a book. If you know 1/8 of a book, you aren't really going to understand the story. So 14.7%, that's maybe considered a little bit lower. And this gets into more statistical fields, but, different R squared values are going to be different by discipline. But in general, you can kind of tell that this top right graph, is pretty spread out. So, the regression equation may fit, but does the variables, or do the variables, tell the whole story? No. It tells a part of the story, but not necessarily the full story. So if we look at the bottom right here, we can see that the R squared says 86.5, and all of these blue dots are very closely, hugging that red line. So there the X variable explains 86.5% of the variability in the Y variable, aka we know 86.5% of the story. The X variable explains 86.5% of the story in our Y variable. So that is very good. That means that our outcome is very highly tied to our X variable. So here's an example of regression. So does poverty percentage predict the number of births for 15 through 17-year-olds? And I'll put a link to where I got this below. So our X variable is going to be poverty percentage, and the Y variable is going to be births for 15 through 17-year-olds. So a positive relationship would mean that as poverty rate increases, birth rate would increase as well. One thing that I failed to mention with regression is you can run random regressions, but the numbers won't necessarily mean anything until you have some sort of hypothesis behind it. So when you're running a regression for a business purpose, maybe you want to see how much, marketing spend relates to how many sales you're going to have. You're not just going to randomly throw two numbers together and hope it spits out something good. You're going to have some sort of hypothesis or some sort of question that your regression equation or your regression analysis is going to be answering. And for this one, maybe there's a hypothesis or a general question that poverty rate is going to predict the number of births for 15 to 17-year-olds. So maybe the hypothesis is that the increase in poverty rate is going to increase the number of births for 15 and 17-year-olds. So let's go ahead and look at the results. So the formula, after we inputted our data into a statistical software or Excel, yes, you can do it in Excel, it gave us a formula of y hat equals 4.267 plus 1.373x. So let's break this down a little bit. We can look at this graph over here. And on our x-axis is poverty percentage. On our y-axis is the number of births for 15 to 17-year-olds. So, if we think back to our high school math class, what is the y-intercept? The y-intercept is the value of y, or the dependent variable, when x, or the independent variable, is 0. So it's kind of like if there's no influence of, our independent variable, how many births would there be? So if a state had 0% poverty, meaning that no one, was impoverished, there would still be an estimated 4.267 births of 15 to 17-year-olds. And this is probably scaled like per 100,000 youth or per 1,000 youth, something like that. So if a state had 0% poverty, there would still be 4.267 births. And how do we interpret this 1.373x? We can interpret it like this. For every 1% increase in poverty percentage, x, birth rate increases by 1.373 units. So for every percent increase in poverty rate, there's going to be an additional 1.373 births for 15 to 17-year-olds. So as poverty rate increases, so do the number of births in these teenagers. So the R squared, or the story, is 53.3%. So poverty percentage, our X variable, explains 53.3% of the variance in birth rate. So the 53.3% means that we have a good portion of the story, but there are likely other variables that impact it. When we're talking about people, or when we're talking about things like social science like this, you're never going to know the full picture. It would take hundreds, thousands, millions of variables, and you still are unlikely to get, an R squared of 100%. That's just never going to happen. But something with 53.3 shows that there is a high, impact on the births 15 to 17 with poverty percentage. So let's go ahead and think about maybe some other variables that would impact, this birth 15 to 17. We can maybe think about high school education. We could think about maybe the family dynamics of, that geographic area. So there are other things that are likely to have an impact and an effect on this birth rate and the poverty percentage relationship. But that's an example of this regression. And I think it's important, especially for this business data analytics class, to look at something from a non-business perspective when applying it to business. Because if we're talking about, marketing spend and, sales, or if we're talking about maybe a relationship with leader and job performance, we sometimes think of it as just some sort of business outcome. But regression can, be applied to literally any field and any type of analysis. So when we're working through, these regression formulas and regression examples, it can be helpful to go back to these real world examples, because sometimes they're a lot easier to understand than business examples. It's kind of nice to have something that you can go back to and tie your mind to when making these connections and relationships. So in simple regression, that is one x variable predicting one y variable. But there's something called multiple regression. So I talked about how poverty percentage explained 53.3% of the variance in birth rate. If I wanted to increase that, or if I wanted to uncover, a bigger picture, maybe we could test, maybe how many of these girls are in high school, or how many are dropouts. Maybe we could test how many have stable families at home. We could test how many have jobs. We could test GPA. We could do a bunch of different things that would likely impact, the birth rate of 15 to 17-year-olds with this poverty, percentage. So we can add additional variables, additional x variables, independent variables that are likely to, impact our dependent variable. So simple regression is one x variable and one y variable. This is simple linear regression. And because the outcome y likely has multiple causes, in reality it's going to have, infinite causes. We can actually add numerous x variables, and this is called multiple regression. When we are using multiple x variables to explain what happens to the one y outcome, one y variable, aka the outcome. And something that we'll also talk about is when you're running these regression analyses, it will give you, if I go back here, it'll give you a coefficient. So this 1.373, it'll say, for every 1.373, or for every percent increase in poverty rate, you're going to increase 1.373 births. But it's also going to give you something called a p-value. And essentially, a p-value is how good that variable is at predicting your outcome variable. So it's kind of, I don't want to say it's like r squared for each individual variable, but it says how important that variable is, or how good that variable is at predicting an outcome variable. But that's something a little bit more detailed for a more advanced lecture. So correlation versus regression. Correlation is a measure of the direction and the strength of the relationship between two variables, and it summarizes the data. And to the statistical measure that is used for correlation is Pearson's R, and it assesses the strength and direction from -1 to +1. So variables can be either positive or negative, and they can either be weak or strong, in that specific direction. And there can be no relationship either. Whereas regression estimates the relationship between two variables. And one way to assess the goodness of fit to a regression model is going to be through r squared, which is actually, for one variable, it is just the square of your correlation coefficient. And then the equation of a line, could be y equals mx plus b, like high school, or, using statistical notation, it could be y hat plus a plus beta x plus error. All right, so we have explained regression from more of a social science standpoint. We are going to apply regression and correlation analysis to some business problems and business techniques. It is a very useful tool for data analysts. And if you have any questions, feel free to comment down below or message or email me. And let's have a great week and happy learning.